Hello, my name is Nicholas Clark. I'm the Agronomy and Nutrient Management Extension Advisor for the University of California Cooperative Extension. I cover the counties of Tulare, Kings, and Fresno. Today I'm going to present on annual crops nutrient management for the Irrigation and Nitrogen Management Plan Grower Self-Certification Continuing Education Seminar. In today's presentation, I'd like to break it down into three main parts. First, I want to discuss some reasons about why nitrogen management planning is important in general. I want you to have a good understanding of why it is that we're going through these exercises. Okay. After that, I'm going to talk about the concept of nitrogen management planning. I'd like for you to be able to understand after this presentation what the basic components of a nitrogen management plan are, how to recognize them when you see them. And then finally, as an example, I'd like to put some of this concept into practice by teaching you how to create a nitrogen budget, and we're going to use the example of a corn silage crop. So let's begin first by talking about some of the reasons why nitrogen management planning is so important. Now, before I really get into discussing the content of this presentation, I'd like you to please take note at the bottom left corner of this slide where it says source material. In each of these slides, when I've borrowed material from other sources, and that happens a lot, I've made my best attempt to show you what the internet link is for that source material if you'd like to check it out for yourself and explore more. In other instances, I've included links to some expanded learning resources. So if you would like to watch more videos or read a little bit more on some of the concepts or ideas that I'm presenting, you have that information at your fingertips just by following the links at the bottom left corner of each respective slide. Now, the reasons that I'm going to discuss about why nitrogen management planning is so important following this and a couple of others are not listed in any order of importance. In my opinion, they're all equally important. They play major roles in determining why nitrogen management planning is so important for all of us. And I'll try to keep them to the context of agricultural production. So to begin with, nitrogen is the single most limiting plant essential element worldwide, and that goes for natural ecosystems as well as agricultural production systems. Plants, as you might know, require 17 essential elements. These are elements that the plant needs in order to grow, function, and reproduce properly. Nitrogen, of course, is one of those essential plant elements, and to say that nitrogen is one of the most limiting essential plant elements is the same thing as saying that in most cases around the world, whenever nitrogen is added to a system, including agricultural production systems, those plants perform better in either their growth or their function or their reproduction or any combination of those. This graph that I'm presenting on this slide is a rather popular depiction of what the world would look like that we live in today had the Haber-Bosch process, which was a very innovative way of creating synthetic nitrogen fertilizer, if that had never been invented. In the gray portion of the gray shaded area of the graph is a projection of what percent of our population on Earth today is fed by agricultural production that is not supported by the synthetic fertilizers that the Haber-Bosch process brought about. And then the red shaded area of the graph shows us where we are today and estimates how much of the world is fed just by the invention of that fertilizer process. It looks like to be about half. Nitrogen is all around us. You've probably heard that it makes up most of the mass in our atmosphere. It's about 70% of the air that we breathe. Nitrogen is all around us, but it's also hard to pin down because it's constantly moving in what we call the nitrogen cycle. Nitrogen is very highly reactive with the environment around it, which means that it's constantly going from one chemical form to the other. Very common forms that we find in agricultural systems are nitrate, nitrite, ammonia and ammonium, dinitrogen gas, which is the nitrogen that you breathe and that rhizobium bacteria will fix for plants. Have you ever heard of nitrogen fixation? That's the form of nitrogen that becomes fixed. There's nitrous oxide, which is a greenhouse gas, urea, and then there's organic nitrogen, nitrogen that's bound up in organic molecules in the soil. A lot of these shifts from one form of nitrogen to the other in agricultural systems are mediated by microbial activity in the soil. Other factors which contribute greatly to the reaction of one form of nitrogen and formation of it into another are pH, soil moisture, and temperature. I won't go into all of the details in the nitrogen cycle that are depicted in this chart, but I would like to briefly point out a couple of the very common loss pathways of nitrogen when we're talking about agricultural production. First of all, loss simply means that the nitrogen that is applied or is within the system is not utilized by the plant. It finds itself outside of the agricultural production system. A couple of very common loss pathways are, for example, leaching, such as when nitrates and nitrites move below the root zone with the flow of water. There's also denitrification, when nitrates under anaerobic conditions are converted by microbes back to dinitrogen gas or nitrogen oxide. And then if you notice in the very center of the graph, the process labeled mineralization, that's the conversion of organic forms of nitrogen into ammonium, which is usable by plants. But what's not depicted here is a process that we call immobilization, which is just the reverse of mineralization, where previously plant available form of nitrogen, such as ammonium, is consumed by microbes and bound up within their microbial bodies and now not available to plants. Another form of nitrogen loss from the agricultural system that is similar to denitrification but not the same thing is volatilization of ammonia gas. It's still a loss of nitrogen in a gas form, but instead of being mediated by microbial reactions, it's more mediated by soil pH. What I really hope that you get away from this slide is not a photographic memory of all of the different pathways of the nitrogen cycle, but more a sense of how reactive nitrogen is. I like to compare it to driving. There are a million things that need to be paid attention to, and probably 100 different ways to get to one place, but ultimately we're trying to get to one destination. And you have to consider that there are a lot of factors pulling you in many different ways. Of course, another very important reason to pay attention to nitrogen management is that it's simply economical. As one of my close peers, who is also a farmer, said to me once, I don't farm for practice. It's very important for all of us to consider that the cost of nitrogen has gone up significantly in very recent history. And that certainly has an economic toll on producers. Pay attention to this graph, for instance, which shows the price of select nitrogen fertilizers over a 10-year period from 2005 until 2014. This data comes from the United States Department of Agricultural Department of Agriculture's Economic Research Service. There's a lot of lines on here, but one thing that is very obvious if you follow any of these prices is that from 2005 until 2014, the price of fertilizers has essentially doubled. That is not an insignificant increase in price. Now, what does the doubling of a price really mean out of context? Could it just be regular inflation? Of course, but I'd like you to pay attention to this graph, which depicts a comparison of prices paid on farm and prices received for goods over a 10-year period. More recently, from 2011 until 2021, you can see that the prices paid with the base price in 2011 on farms has increased by about 10%, although the prices received on farms has fallen since 2011. So I hope you can recognize by now, of course, that not only is the price of fertilizer increasing, but prices received on farms is going down, which means that economically, a producer needs to be more economically prudent when purchasing fertilizers and applying fertilizers in order to remain economically viable. If you recall some of the earlier slides, the situation seems to become even more complicated when we consider that nitrogen is very difficult to pin down in the environment. One of the ways, of course, that producers have dealt with decreasing prices received and the increased cost of goods has been to simply produce more, become more efficient with production, making the land simply more productive. As these select graphs from Iowa State show, over a 40-year course, some common staple commodities, the yield has increased drastically. This is not just the product of more efficient nutrient use, but also just improved agronomic practices, improved crop varieties, improved irrigation management, improved pest management, so on and so forth. Now, when we talk about nitrogen and the environment, as I did in an earlier slide when discussing the nitrogen cycle and loss pathways, it's also important to recognize that when nitrogen leaves the agricultural production system, it can have very profound effects on natural ecosystems and human health. Something that I think is very important for all of us to remember is that in a civilized society where we depend on agriculture for production of our food, our fiber, and some of our fuels, farmers are in fact the very first in line in our society to protect the quality of our environment. So it's very important that together we educate ourselves and become better practitioners of how to utilize nitrogen more efficiently, one way through nitrogen management planning, in order to minimize the loss of nitrogen to the environment outside of the agricultural production system, in order to then minimize any of the potential negative effects that nitrogen losses to the environment might have on natural ecosystems and human health. This graph, for instance, depicts data from the U.S. Geological Service that color codes the nitrate or the nitrogen concentration of groundwater tested from wells in centered around the southern San Joaquin Valley. You can recognize, for instance, by the yellow shapes that there are a number of wells that have exceeded the federal limits on the maximum contamination level of nitrogen, and this is often thought to be considered a level at which nitrogen in drinking water can be hazardous to a vulnerable subset of human population, and is also a concentration that is highly regulated by the federal government. The significance of this point, of course, is, as you remember, I pointed out that one of the lost pathways of nitrogen from the agricultural production system is through leaching of nitrate and nitrite as it moves below the root zone of crops with applied water. Any improvement in nitrogen management which minimizes the movement of nitrate and nitrite below the root zone of agricultural crops, of course, is going to have a beneficial impact on groundwater quality going forward. And of course, as mentioned before, agricultural nitrogen can also be lost to the atmosphere through a process called denitrification. The graph in the center of the slide shows two of the major pathways by which agricultural nitrogen is lost to the environment through denitrification. In the left circle, you can see that through the process of nitrification, which is the conversion of ammonium nitrogen to nitrate, nitrite itself can be converted to nitrous oxide and lost to the environment. That's from incomplete nitrification. And then in the blue oval in the graph, you see full-on denitrification, which is also a microbial process that occurs under anaerobic conditions when nitrate itself is converted to nitrous oxide, or in more complete situations, dinitrogen gas. Dinitrogen gas, of course, is rather inert and, as mentioned before, makes up most of the mass in the air that we breathe. Nitrous oxide, however, is recognized as a very important and potent greenhouse gas. Denitrification can be managed and lessened in agricultural systems through management of organic matter inputs, fertilizer inputs, and improvement of soil tilth and drainage. Generally, incorporation of things like manure into the soil after they've been applied will lessen the amount of nitrous oxide that is emitted. And on the other hand, improvement of soil drainage, so reducing the amount of time that soils are saturated, can also reduce the amount of nitrate that is denitrified and lost to the environment in the form of nitrous oxide. Not only is this, of course, better for environmental quality, but better for economic viability of agricultural production, as less nitrogen is lost from the system and more is available to be utilized by the crop. And finally, a reason that I'm not going to go into very much detail about, that reason why nitrogen management and planning is important to pay attention to, and also probably the major reason why most are viewing this seminar series, is that nitrogen is highly regulated in California. We have many agencies that regulate nitrogen and how it's used and moves in agricultural systems and the environment. And just as an example of how nitrogen is regulated in California, we can take note of 4 major California regulations on agricultural nitrogen in groundwater, many of which we're probably all familiar with. The Irrigated Lands Regulatory Program, which regulates the use of nitrogen in irrigated agriculture in California. There's the Dairy General Order, which regulates, among other things, the use of nitrogen in agricultural production systems where dairy manure is applied. The CV Salts Program, which resulted in amendments to the water quality plans and have a component called the Salt and Nitrate Management Plan, also regulate and propose to regulate the nitrate in groundwater and surface water discharges from agriculture. And finally, the Sustainable Groundwater Management Act also lists water quality degradation as an undesirable result, which of course would include any degradation of groundwater quality or surface water quality by addition of nitrogen from agriculture. Now that we've gone over some very general reasons about why nutrient management planning is important, I'd like to go a little bit closer to the ground and talk specifically about nitrogen management planning and get into the conceptual parts of it. Look more at what are the components that make up a nitrogen management plan. One thing that I would like to clear up before I continue is when I talk about a nitrogen management plan in this presentation, I'm not referring to any of the regulatory templates that some of you might be familiar with, which are required to be filled out. I'm really talking about nitrogen management planning literally. What I'm about to tell you, would be true with or without regulation. The concepts that I want to share with you right now will help anybody in producing crops and using nitrogen if thought of in the following way that I'm going to present. So I like to think of nitrogen management plan as consisting of four main elements that make up the plan. I like to start in the top left of this graphic with the goal. The goal is set by where you would like to be, how much nitrogen you would like to get out of the system, or that can be translated in terms of how much yield do you expect out of the system. Going clockwise in this example, the next element of the plan is the budget. And I think it's an apt analogy because in a nitrogen management budget, we need to tally what our credits are, what we already have, for instance, what we expect to gain or what we would like to be left with after the plan is executed, and then finally, what we would need to put into the budget. It's more a tally or a ledger of nitrogen that is in the system, moving in the system, and moving out of the system. Continuing clockwise with the plan, the next element is the application of the plan. That means, what do you do with the budget that you've created? How much nitrogen do you apply as a fertilizer or as an organic amendment, for instance? Continuing clockwise with the plan, the final element in this cycle is to monitor and adjust. That means that after fertilizer application has been made, for instance, the plan is not over with. It's important to monitor the progress and the impacts of that application by doing testing of the field, testing crop tissues, testing soils to see what are the impacts of that fertilization, and then making decisions based on that information, ultimately deciding if the plan was successful or if it needs to be adjusted, readjusting that goal, and then starting sometimes right back in square one again, either within the season or for the next year. So when we talk about setting a goal in a nutrient management plan, really what we're talking about is setting the expectations for nutrient use of a crop. There are many factors that contribute to the nutrient use of a crop, but generally the best place to start in defining a goal for nutrient use is understanding what the yield is of that crop. There are many factors that go into the final yield of a given crop, but ultimately it's the final yield that really defines how much of a specific nutrient is used or removed in harvest. It's also important to recognize that yield is not a single factor for any given crop. We'll get more into variability of yield later on in this presentation, but I presented this graph on this slide just to demonstrate the point that between counties, for instance, for corn and alfalfa hay in the San Joaquin Valley,
you can recognize that there's quite a bit of variability in between years and in between counties. And that's not even really the most specific level that a nutrient management practitioner should pay attention to, but we'll get more into that later. Once the yield goal is set, then the next important question is, what are the actual nutrient requirements for that crop at a certain yield level? There are several tools out there on the internet today that present the user or the visitor of those websites with an interface that would allow you to input information about a specific crop. Mainly, though, they base their estimations of nutrient use or nutrient removal during harvest based on the yield. Here are just pictures of a couple of examples of some common resources that help nutrient management practitioners estimate what the nutrient use is for a range of crops based on their yield level. And you can see the web links for these resources and in the bottom left-hand corner of this slide, of course. And these are not the only tools, but some very prominent ones that exist out there. However, regardless of the tool, they all generally do the same thing. They tell you how much of a certain nutrient is used by a certain unit of yield. So then, as a nutrient management practitioner, once you're armed with the information of what your yield level expectation is and what the nutrient use factor is for that crop and that yield level, then it's just a matter of simple arithmetic to come up with an expectation for how much of a given nutrient will be used. In this example, shown in this table, I'm showing a range of nitrogen that would be removed with the harvest of silage corn. In the very left column of the table, I'm showing you a list of the information sources shown on the previous slide. So you can see that even in between information sources, there's often some variation in the nutrients that are predicted to be used. My preference for crops grown in California would be the report produced by Daniel Geisler. That's that middle row there. And that preference is mainly because the data tends to be updated very regularly. The report is very transparent about where the data comes from and what the quality of the data is, so what the variability is within that data. You can view all of that information right in the report. And the tendency in the report is for data that comes from California production to be privileged over data that comes from elsewhere in the country. So not only is the information in that report very up to date, but it also incorporates the growing conditions, management practices, and cultivars for the crops that are most commonly grown in California. So then in the right three columns of this table, I've shown you a range of yields for silage corn expressed in tons per acre, 25, 30, and 35 tons per acre. And then when you multiply that yield level by the nitrogen removal factor that's reported in each of those sources, you simply come up with a product. And that product, so for instance, 30 tons of corn as expected nitrogen to be removed, reported in the Daniel Geisler report, you would expect that 227 pounds of nitrogen would be removed every acre for 30-ton corn yield. So that was the gist of what a nutrient management goal is and how they're set. Now we're going to talk generally about a nutrient budget. Just like a nutrient goal, the nutrient budget is not a static document. It's not something that can be handed down. It needs to be recreated anew for each field and for each crop. But think it is true that each nutrient budget does have the same major components or major categories each time. Those major categories are the credits, the inputs, and the outputs. Nutrient credits are the things that already exist in the field, such as residual soil nitrogen. So we're talking about nitrogen in this case. Nitrogen that will be available to your crop that comes from previous crop residue that's left over in the field. Irrigating with water that has nitrate in it is also a credit to your crop. In other words, credits are those things that give your crop nutrient without you having to actually purchase fertilizer or an amendment for that crop. Then there are the inputs. These are the things that you would actually buy and put into the field in order to provide nutrients for that crop. Finally, there are the outputs. What do you get as a sum result of the credits and the inputs, then of course all of the other management practices that you invest into your crop? And generally, the outputs can be listed as the yield. So what do you pull off of the field? And then what is the inefficiency? So not every input and every credit that is available to the crop will necessarily come off in yield or just be left over in residue. Sometimes nutrients are lost to the environment, and we need to take account for that also when creating a budget. This slide just presents a graphic which shows you another way to think about the budget. It has all the same components, it's just presented in a different way. In the top part of the equation, you can see fertilizer plus soil plus water. Fertilizer is just another way of saying inputs, something you buy in order to provide nutrients to your crop. And then soil plus water. That's showing you where nutrients come in as a credit, what's left over in the soil, what's coming in with irrigation water. Fertilizer plus soil plus water, in other words, inputs plus credits, equal outputs, or harvest plus inefficiency. Now, in this graphic, you can see some arrows that emanate from inefficiency. One arrow, the blue arrow going down, is supposed to represent inefficiency of nutrients that leave the system that are not used by the crop. Either they leave through volatilization, they might be leached, they might be lost through runoff or wind erosion. And then another arrow points up, the red arrow pointing right back to the soil, which is also red, to indicate that even though a nutrient is not used by the crop, it's not necessarily lost from the agricultural production system. It might just be carried over in the soil and thus used or counted as a credit for the next or following crop. I would like to emphasize here that as we're talking about inefficiency, I really want to point out that inefficiency is not something that is unique to agricultural systems. There really is no such thing as a perfect system or a system that is 100% efficient. It just simply doesn't exist. What's most important about inefficiencies is that we understand them, what causes it, and how to manage it. I'm going to return to nutrient budget later in the presentation when we go into more detail in the example of putting together a nutrient budget. Now we'll move on to the application component of a nutrient management plan. When we move from the budget phase of a plan into the application phase of a nutrient plan, we're really shifting gears here. This is where the rubber meets the road, so to speak. If the first two parts, the goal and the budget of a nutrient management plan, are the pen and paper, when we shift into the application phase, we're really talking about soil and plow. These are the things that you have to actually do to your field. Of course, when nutrients are applied to the field, we have to consider their efficiency. There's that word again, efficiency. It should be noted that since I'm repeating it, it's something important to pay attention to. In the wheel graphic on the right, which I borrowed from my colleague Daniel Geisler, You're probably familiar with the shapes that are represented in different shades of green: nitrogen rate, nitrogen time, nitrogen place, and nitrogen source. These represent the 4 R's of nutrient stewardship: right rate, right time, right place, and right source of nutrient placement. All of these factors contribute to the efficiency of which nutrient is used by a crop. Daniel, of course, wanted to emphasize that in irrigated agriculture, which is most relevant in California, that the water rate and the water timing are also important factors that contribute to the efficiency of nutrient use. I'd like to return to the concept of the 4 R's for just a second and present them to you in the form of questions that we might ask in order to determine what the right part is of each of those categories. So, for instance, when we're trying to figure out what the right rate of a fertilizer is, questions that you might ask are: is this enough fertilizer to meet my crop demand, the goal that we set earlier? And is it enough fertilizer to overcome not just the demand of the crop, but whatever the inefficiencies in that system already are? You have to apply enough to meet the crop yield demand as well as cover the inefficiencies, whatever is going to be lost in the system or not utilized directly by the crop. When we talk about the right timing of a fertilizer application, uh, primarily we're asking, am I applying the fertilizer at the time that the crop needs it the most? Does it make sense to split applications of a fertilizer, or can this fertilizer be placed all at once during the crop growing season? The right place, we really want to know, does the crop have access to these nutrients? So, for example, are the nutrients close to where the roots are going to access them? Will the roots grow into where these nutrients are placed? Are the nutrients expected to move away from where the roots are? And also, we have to be cognizant of whether or not there's going to be an injury to roots. Sometimes banded fertilizers, potassium, for instance, might have a salt index that's injurious to young crop roots. We have to be aware of that as well. Then, when we talk about the right source, we're really asking, are these nutrients going to be available to the plant? Essential elements for plants, of course, are not available to the plant in every chemical form. So we need to be aware of what those forms are of the nutrients and have an understanding of how those forms will change with the chemistry and the microbiology of the soil to become plant available. Also, we might be asking, are there going to be any negative interactions with the environment with this source? For instance, is it a fertilizer that we might expect to volatilize, like placing urea on the surface in a high pH soil without irrigating it in promptly after, for instance, might be a negative interaction with the environment. Now that we've gone through the major components of actually applying nutrients, we need to move on to the next phase of the nutrient management plan, which is to monitor and adjust. That is to say, it's not enough to just put fertilizer out, but we want to follow up and measure the success or perhaps even failure of a nutrient application so that we can then adjust management practices in order to optimize the yield output of the crop. Monitoring your field after you've made a nutrient application is something that can be continuous throughout a growing season, or it can just be done at a single or maybe a couple of times in the field. The most important thing to consider when determining how often monitoring should occur is whether or not what you're monitoring is going to lead to actionable information. So, for instance, it would make sense in growing a corn crop that you test the soil just previous to when the crop is going to enter a very rapid growth phase, when the crop would have a very high rate of demand of nutrients, in order to make an adjustment to the soil fertility before the crop really needs all of those nutrients. You would want to determine whether or not any of them are lacking. Other important considerations when monitoring your field after nutrient application is to consider the representativeness of the sample. That is where you're sampling, does it actually tell the story of the bulk of the field or the part of the field that you would like to take action on or learn more about? And of course, the other component that's critical to consider when monitoring the field is, have the sampling, the defined sampling protocols been followed? There are defined protocols for when to collect a sample, how to collect a sample, how many should be collected, from where they should be collected, and then how those samples should be handled after they've been collected before they're sent to a laboratory for analysis. There's a saying that describes what your expectations should be of results from an analysis. It says garbage in, garbage out. That means uh, uh, that whatever the quality of the information you input into an analysis, that is going to define the quality of information you get out of the analysis. In other words, if you were to collect soil samples from a field from an area that is not representative of that field, you should not expect the results to represent that entire field. It's only going to represent the area that you sampled from. The graphic shown on this slide presents an example of a stratified soil sampling plan in a field that has two different soil series. The assumption is that the field can be divided into two different productivity zones or two different soil zones where we would expect the results to be different based on the difference in soil series. The white dots and arrows represent from where a nutrient management practitioner should take cores of soil in order to mix into a composite or just a single soil sample that can be submitted to the laboratory and represent the soil parameters for that entire area. The resource in the bottom left, linked in the bottom left of this slide, lead to the California Department of Food and Agriculture's Fertilizer Research Education Program's website called the Fertilization Guidelines, and specifically document produced which describes how to come up with a soil sampling plan that is representative of the area that you're trying to learn about. The soil in the field, of course, is not the only thing that we can monitor by sampling. It's also possible to monitor the success of a nutrient application by testing crop tissue. All of the same rules apply to sampling crop tissue as are relevant in sampling soil. The sample should be representative. It needs to be taken at an appropriate time and from the correct part of a plant and an ideal number of plants in order for the results from the analysis to be valid. In the graphic that I'm showing here, it's just an example of a protocol for sampling alfalfa tissue that demonstrates the different parts of the plant and how they represent known critical values, which I'll get into in a second, of specific nutrients. Not all parts of the plant, in other words, are going to give us the information we want about all nutrients. We need to be aware of that as well. There is an advantage that in sampling plant tissue that you do not necessarily have when you sample soil, and it's that Since it's really the production of plants that we are most concerned about ultimately at the end of the day, sampling the plant tissue is a way of telling us what it is that the plant is seeing as a sum total of all of our management practices, as well as what the plant is seeing in the soil. So testing the soil will tell you to some degree what nutrients exist in the soil. Testing the plant for those nutrients, on the other hand, tells us what's actually available to the plant. What is the plant able to extract from the soil? Of course, there are many factors that will affect nutrient availability, but if we want to have a more precise idea of what nutrients are available to the plant, that is one advantage that sampling plant tissue offers us over sampling soil. That's not to say that one could replace the other. They should be used in conjunction whenever possible, but that is a critical difference between the two sampling methods. Once a sample is submitted to the laboratory, they run the appropriate analyses on the sample, and then oftentimes will return a report to you which includes not only the values that they found when they tested the sample, but also a recommendation for what to do, usually in the form of an amendment, addition, or a fertilization for a specific nutrient. Those recommendations are not arbitrary. They come based on known guidelines for the sample type and the crop type, and oftentimes with a little more specific information about from when the sample was taken relating to the crop growth stage. Sometimes the guidelines that laboratories are using are what we call critical values. Critical values, either for soil or for plant tissue, are concentrations of a given nutrient in a certain plant part at a certain growth stage of that plant that tell you whether or not that nutrient is deficient in the plant, whether or not it's sufficient in the plant, or in excess in the plant. Those ranges, of course, will then translate to a likelihood that fertilization with that specific nutrient will lead to a desirable response in the crop. In this example that I'm presenting here in this table, we're looking at critical values for soil tests of phosphorus and potassium for a certain number of annual crops. What you'll notice is that for either of these nutrients, either phosphorus or potassium, and for all of the crops, in the leftmost column, that'll likely, meaning a fertilizer response is likely, you'll notice that the values are inequalities. So for corn, for instance, a phosphorus yield response is likely when Olsen phosphorus in soil is less than 6 parts per million. And somewhere in the range between 6 and 12 parts per million Olsen phosphorus in the soil for corn, we would say that that is a sufficiency range. You want to have your soil phosphorus somewhere in between those two values. Of course, then if Olsen phosphorus in corn soil is above 12 parts per million, it's less likely or not likely at all that adding phosphorus fertilizer to the soil is going to give you a fertilizer benefit to that corn. It's critical to understand that when we talk about these values, these critical levels of nutrients, either in soil or in plant tissue, they're not directly translatable to how many nutrients in terms of pounds, for instance, are actually in the soil or in the plant or available to the plant. They're more of an index that it's like taking somebody's temperature. It gives you an idea of whether or not they're sick or healthy. This is exactly the type of information that nutrient management practitioners will use when monitoring the progress of a crop in order to make a decision about whether or not the nutrient management plan needs to be adjusted, either by withholding a planned fertilizer application or adding a fertilizer application to the plan because all of a sudden the crop is unexpectedly showing a nutrient deficiency. By now, you should be familiar with all four of the components that make up a nutrient management plan. Now we can move on to actually putting one of these components into practice. We're going to go through an example of how to create a nitrogen budget for a silage corn crop. As we go through the example of how to create a nitrogen budget for a silage corn crop, I'm going to revisit some of the concepts that we talked about earlier, but of course we'll get into much more detail and have some tangible examples to think about in order to illustrate the points. Just as a quick review, before we come up with the nutrient budget, we need to understand what the yield goal is. And I'll mention here, or reiterate here, that a yield goal is always site-specific. Earlier, we looked at yield variability between counties over a number of years. Here in this graphic, we're looking at yield variation across years just in one county, Tulare County, for silage corn. One thing to note is that this graph could easily be labeled, field 1A silage corn yield variety for a given farm. The point being that yield does not just vary from year to year, but it also varies field to field. We also need to pay attention to the specific hybrid that we're planting. Some hybrids have different yield potentials. Speaking of corn, and early relative maturity corn tends to have a lower yield potential than a later relative maturity corn. Depending on whether or not the crop is a transgenic crop and has technologies built into it, such as pest resistance or herbicide resistance, might also help determine the yield expectation for that given field. If there's a known particular pest problem or weed pressure problem, and sometimes specific corn hybrid might be more or less salinity tolerant. So all of these things need to be known before we set a yield goal for a given field and crop. So we're going to use this imaginary field. Say that 4 years ago, corn was grown on this field and it yielded pretty well, 32 tons per acre. We're going to assume that this year we're planting that hybrid or a very similar hybrid in terms of relative maturity. This particular field is coming out of a 3-year stand of alfalfa hay, and before that hay there has been a history of dairy manure applications to the field. This particular soil type, Colpine loam, which is a typical loam in the southern San Joaquin Valley, is very uniform. It's deep and also well drained. Chemically, it has a neutral pH. It's just over 7, low salinity, below 1 decisiemen per meter in the of electrical conductivity in the saturated paste extract of the soil. And the soil organic matter is about 2%. It's not terribly high, but in the southern San Joaquin Valley on mineral soils, it does represent the higher end of the range of soil organic matter contents. So I'm going to go ahead and say on this field that yield expectation with all of that information of 32 tons per acre is a reasonable goal to set. I don't think we need to augment our yield goal with all of this information. There's not expected to be any problems with drainage or waterlogging that might tie up nutrients. Don't seem to be any chemical factors that would limit yield, like salinity. And we would expect the background fertility to be rather moderate or high coming out of alfalfa and having that history of dairy manure. And the evidence shows that we can get 32 tons per acre out of this field based on record from 4 years ago with corn. So we're going to go with that number. Now here, revisiting the idea of setting goals, we need to translate our yield expectation for this field into a seasonal crop nitrogen requirement. And keep in mind, we're not talking about the fertilizer requirement. We're talking about how much nutrient the crop itself needs, not what we need to apply in order to supply the crop with that nutrient. So in this example, we're using another resource that I'm just now introducing that comes from the Western Plant Health Association. I have a published edition of the Western Fertilizer Handbook. Currently, they're in their 9th edition. So this fertilizer factor for nitrogen, for instance, for silage corn, comes from that resource. You can see in the table that I presented here that for every ton of yield of silage corn, we would expect the harvest to remove 8.3 pounds of nitrogen. So then by simple arithmetic, like we did before, if we're expecting a 32 ton per acre yield of the silage corn, the math tells us that we should expect 266 pounds of nitrogen to be removed in that harvest. That is a very good number to start with in our budget in terms of a crop nitrogen requirement. So now, bringing us back to the concept of actually creating a crop nitrogen budget, you should recognize this graphic from earlier. We're going to fill it out and then on the right-hand side, and then detail the information about how we're doing that on the left-hand side of the slide here. So as we just figured out, our particular field needs 266 pounds of nitrogen just for the crop to be able to remove in harvest. And if you look over on the right, that's what we're considering to be our yield output. We're going to sort of start backwards in our budget. We're going to start with the endpoint and work our way up to what we need to actually put into the field. So let's start determining what our nitrogen credits in this field are. We'll start with pre-plant soil residual nitrate. And we're going to take the residual soil nitrate of the top 2 feet of soil. If you notice in the credits box, I've entered the information here that we tested at 10 parts per million nitrate nitrogen in just the top 2 feet of soil. So now we want to calculate what the fertilizer equivalency is of that 10 parts per million nitrate in the top 2 feet of soil. You take that value, 10 parts per million, and then we multiply it by a factor of 4 because there are approximately 4 million pounds of soil in every acre foot of soil. And since we're looking at the top 2 feet of soil, we'll multiply that again by 2 in order to know what the pounds of nitrate nitrogen are in the top 2 feet of soil. 10 times 4 times 2 equals 80 pounds of nitrogen, and that's for every acre in the top 2 feet of soil. However, not all of those pounds of nitrate nitrogen are going to be available to the crop because, of course, the roots do not occupy all of that volume. We'll multiply by a conservative efficiency factor of 70%. That's based on the assumption that in the top foot, about 40% of the effective roots of the plant can be found, and in the second foot, about 30% of the effective roots of the plant can be found. So we'll say conservatively that the plant will be able to utilize 70% of that nitrogen there. So the 80 pounds of nitrogen per acre that exists there times an efficiency factor of 70% or 0.7 leads us to 56 pounds of nitrogen in the nitrate form per acre as a credit just in the soil. We also want to give credit to the nitrogen which will become available through the process of mineralization. If you remember from very, very early on in the presentation, mineralization is the microbial process that occurs in soil whereby the nitrogen that is bound in organic molecules is decomposed by microbes and converted to the ammonium form of nitrogen, which is available to plants. Now, we know through studies that Central Valley mineral soil can mineralize about 80 pounds of nitrogen per acre per year in the top foot of soil. That's over the entire year, but here in this case, we're not growing a crop for the entire year. So we need to figure out how much nitrogen is being mineralized just during the growing season. We're going to say that this crop is planted on April 15, and we have an estimated harvest date of August 15, about a 120-day corn hybrid. Now, based on a tool that my colleague Daniel Geisler has created, it's a tomato nitrogen fertilizer calculator, and you can find access to that tool by following the link on the bottom left corner of this slide. We can assume that between the dates of April 15 and August 15, that of that 80 pounds we would expect to mineralize per year, we're only going to get about 40 pounds of it within that window. Again, that's based on a study published in the literature for this area of the country that basically determines how much nitrogen is mineralized, not just over time, but on the basis of what the typical soil moisture is and what the ambient air temperature and soil temperatures are. Also very important factors that drive nitrogen mineralization and other soil microbial biological processes. So here in this case, as another credit, we're going to add 40 pounds of nitrogen per acre to our crop. And in this example, the final credit that we're going to give to our crop in the nitrogen budget is to irrigation water. This particular field, for example, doesn't have access to ditch water from an irrigation district, so they rely in this field completely upon irrigation by a groundwater well. Upon testing that groundwater quality, we determined that the concentration of nitrate nitrogen is 2 parts per million. Now that we know what the concentration of nitrate nitrogen is in that field, we need to consider how much water is being applied and how much is actually going to be used by the crop in order to come up with a credit of nitrate nitrogen to that crop. There's a relatively simple formula in order to calculate how much nitrate nitrogen exists in a volume of water, and the formula is whatever the parts per million of nitrate nitrogen test are times 0.23 will equal the pounds of nitrate nitrogen in every acre inch of irrigation water. So in this case, 2 parts per million nitrate nitrogen in 1 acre inch of irrigation water equals 0.46 pounds of nitrate nitrogen. Now, when we're crediting nitrate nitrogen through irrigation water to a crop, we don't want to account for every pound that's applied in irrigation water. We only want to account for the water that's actually used by the crop. We can't give credit, of course, to nitrate nitrogen that is not actually utilized by the crop and moves with irrigation water below the root zone. So we're going to only count the crop evapotranspiration water. Now we know through research, again, that corn silage crop evapotranspiration equals about 1 acre inch for every ton of corn silage. Remember that in this example, our estimated yield or our yield goal is 32 tons of corn silage. Multiply it then by that 1 acre inch for every ton of silage, and then multiply it by the 0.46 pounds of nitrate nitrogen in every acre inch of water, and what we come up with is a credit of about 15 pounds of nitrate nitrogen per acre that is coming in just through the irrigation water that we can give to our crop in the credits column. So now that we've figured out our nitrogen credits within our budget, we're going to move on to figuring out what the nitrogen inputs are. Now, the nitrogen inputs simply equal the outputs minus the credits. Outputs specifically here meaning yield, or even more precisely, the total crop nitrogen requirement. Not the fertilizer requirement, but the crop requirement. Again, what we expect to remove in yield. And then minus the credits, everything that we just figured out. There's an asterisk up here next to this very simplified equation to draw your attention to the fact that we still do need to account for nitrogen use efficiency of each of the inputs. We can't simply do the math and then expect that that is going to be the exact fertilizer requirement. We have to remember that when we place it, the form we use, if you just recall back to those, the 4 R's, we know that they're not all used efficiently, so we'll probably have to add a little bit more fertilizer in order to meet our crop demand. Here in the inputs column, I've listed some examples of inputs that are available to this farmer for this particular field. We have dairy manure that comes in the form of corral scrapings. Those are solid manure. Have access to fertilizer injector to side dress UAN 32 fertilizer, and can also water run ammonium during an irrigation. If you look on the left of the slide, I have sort of a tally of everything that we've already figured out already. Remember that in our outputs, we're expecting the crop to remove 266 pounds of nitrogen per acre. And then we've given credit to soil nitrate, the soil organic matter mineralization during the growing season, and the irrigation water that we expect the crop to use through evapotranspiration. So now we're left at this point with the task of calculating the remaining crop nitrogen requirement. So the inputs is going to equal 266 pounds, that's our expected output, minus the sum of all of these credits, and it leaves us with remaining crop nitrogen requirement of 155 pounds of nitrogen per acre. Remember, this is the crop nitrogen requirement, not the fertilizer requirement, and we still need to take into account the inefficiency of that 155 pounds that we would meet through applying fertilizer or manure. Now we're going to move on to another input that this farmer wants to apply to their field. It's corral scraped manure. They're going to apply it at a rate of 10 tons per acre, and they'll be applying it at the 75% moisture that it's found in the stockpiles. And they sent a test to or a sample of this manure to the laboratory, and it was tested as is at that 75% moisture, and the results came back that was 1% total nitrogen. A lot of corral scrape manure, the total nitrogen is usually represented by about 90% of in the organic fraction. So just for the sake of ease in this example, we're not going to consider any of the ammonia nitrogen or plant nitrogen that's available, but in reality, that would also need to be taken into account. In this case, we're going to simplify it just by looking at the organic nitrogen. So let's move over to the left-hand side of the slide. We've got 10 tons of manure. 1% of it is nitrogen, so we're doing 10 tons, and then of course to convert to pounds, we'll multiply by 2,000, and then multiply by a percentage decimal fraction, 0.01, which represents 1%, and it tells us that in that manure that's applied in 10 tons for every acre, we're applying about 200 pounds of total nitrogen. We're assuming all of it is organic. However, not all of that nitrogen is going to become plant available in the crop season. Some research that has been done in the past in California by Stu Pettigrove and some colleagues has shown that for corral scrape manure, only about 25% of that organic nitrogen becomes available or is mineralized within the first year. So we take that should, sorry about that. You take that 200 pounds of nitrogen, multiply it by the 25% or the decimal fraction 0.25, and we come up with 50 pounds of nitrogen per acre will become plant available from that pre-plant manure application. This resource in the bottom left corner of the slide will take you to some list of resources related to manure nutrient management. So now that we've calculated our credits and then determined what nitrogen is going to be available to the plant from the input of solid manure incorporated pre-plant, what's left for us now is to calculate the remaining crop nitrogen requirement that needs to be met by fertilizer. So we'll take our initial goal of 266 pounds and then subtract our credits of 111 pounds and our manure nitrogen availability of 50 pounds, and what we're left to make up by fertilizer for the crop nitrogen requirement is 105 pounds of nitrogen per acre. Now, it's important to note again that crop nitrogen requirement might not simply be met by one fertilizer application of 105 pounds of nitrogen, but rather nitrogen application rate and timing should be determined based on soil and tissue testing, as we mentioned before. For budgeting purposes, to get a good idea of how much fertilizer might actually need to be applied in order to meet the natural inefficiencies of applying nitrogen fertilizer to crops, we'll apply an efficiency factor of 70% of crop nitrogen utilization. So to apply that 70% efficiency factor to our crop demand of 105 pounds of nitrogen per acre, we'll divide 105 by the decimal fraction for 70%, which is 0.7. That gives us a quotient of 150 pounds of fertilizer. Again, your fertilizer application might be more or less efficient. 70% is about an average of what we expect crop nitrogen utilization to be. So that's just to give you an idea of how much fertilizer you might end up applying. Again, that'll have to be determined by in-season testing of soil and tissue to determine if an application is actually necessary. Here in this slide, what I tried to present is sort of a summary table of everything that we figured out for this crop nitrogen budget. You can see in the left-hand column all the three different categories, with which we should all be very familiar now. The outputs are the goals, credits, and the inputs. And then for each of those categories, the item that we're actually talking about. Okay? And then in the very right column, the values that we have just gone through and figured out. What we're concerned about now is meeting the crop nitrogen requirement with fertilizer. So what do we do at this point? Well, we need to realize that now we're moving on to the phase in the nitrogen management plan of monitoring and adjusting. So we need to test. Keep in mind in this example, the application that we made was pre-plant, so we have plenty of opportunity in terms of time to do testing of soil and plant tissue. This field would be a good candidate looking at the remaining fertilizer or nitrogen requirement for that crop for pre-side dress soil nitrate testing. There are some values that are available that tell you what an appropriate fertilizer application would be based on certain pre-side dress soil nitrate tests. In corn, you have the capability of doing plant tissue testing all the way up until silking in order to make a timely fertilizer application that can correct a nutrient deficiency. So that concludes the presentation. This is a summary slide where I'd like to very briefly review everything that we've gone over. If you remember, we broke this presentation up into three main segments. We talked about the importance of nitrogen management or nutrient management in general. Then we went over all of the concepts of nitrogen management planning, and I hope I instilled the idea that nitrogen management planning is methodical. Then we went on to an example of budgeting, how to actually construct a crop nitrogen budget with specific examples. Regarding the importance of nitrogen management, remember that nitrogen, for instance, is the most limiting plant essential element. It's the most reactive or transient. It moves around a lot in terms of plant essential elements. Stewardship of land, air, and water in terms of protecting the environment are also important reasons to manage nitrogen. And then, of course, regulatory agencies are very interested in nitrogen management and require certain levels of monitoring and reporting and actual management practices. With regard to nitrogen management planning, remember there are four main components of nitrogen management plan. There's the goal, which we set based on data that's available to us, and we also keep reasonable expectations. We budget with available data and then make sound estimations, usually about the efficiency of our credits and inputs. Then we actually make the application. We execute the plan, and we always consider the efficiency of fertilizer and input applications. After an application is made, and we monitor the success of that application by soil and tissue testing, and then we monitor the application of the plan accordingly if it needs to be, and that's always driven by data. That data, of course, needs to be derived from samples that are representative of the area that we're trying to make a decision about. Then when we get to budgeting, it's, in my opinion, easiest to start with the outputs or the goal and then work backwards. You need to give your field credit where it's due, but don't give more credit than you can, and certainly don't discount yourself. Then what's left after determining the goal and what credits can be attributed to that crop in that field, what's remaining is to estimate the needed fertilizer and other inputs that need to be applied. And it's important to remember that usually those application recommendations should be come along with testing and monitoring that goes on in the field. Thank you very much.